This video is going to start looking at kinetics and the factors that affect the rate of a reaction, and then some basic information about reaction rates. Before we totally jump into the different things that can affect the rate of a reaction, it's probably a good idea to get a good working definition of what kinetics is. Kinetics basically is anytime you're looking at the speed or the rate of a reaction under different conditions. So as soon as you hear kinetics, think, okay, we're looking at the rate of a reaction. Any reaction that's thermodynamically favored, and you might say, well, what does that mean? Thermodynamically favored reactions. That means these reactions just happen on their own with no external energy. So if a reaction is thermodynamically favored, that means it can just happen on its own and doesn't need any energy to go. That doesn't mean it's going to be a fast reaction. Right? Some reactions here actually happen within a fraction of a second, like an explosion. All right, boom, it just goes off and the reaction takes place. Other reactions that are thermodynamically favored, like diamond formation, takes millions of years. So just because a reaction is, thermodynamically favored and can happen on its own, doesn't mean the rate of that reaction is going to be really, really fast. But when we're looking at kinetics here, we're going to be studying the rates of reactions. There are a bunch of different things here that can affect the rate of a reaction. And by rate, we mean how fast or slow it's going to go. The first thing that can affect the rate of a reaction is what we call the nature of the reactant. So the physical state of the reactants, for example, if you have reactant particles that can more readily collide, you're going to have a faster reaction rate. For example, you might mix two solids, but they don't react. But if you put both of those solids into water, dissolve them, and then mix the solutions, the reaction might rapidly occur and you see the precipitate forming. All right, so you should understand here that a solution would have a faster rate than, say, a solid. If the materials here, the substances reacting, can more readily collide, you're going to see a faster reaction. And then sometimes here, what we'll call the chemical identity, opposite charges would react more quickly. If you have a lot more bonds to break, a rate might be a little bit slower. And then substances here with stronger bonds might react slower as well. All right, so we just call this the nature of the reactants. If you have these substances readily available to react, they're going to react with a faster rate. The next thing that affects the rate of a reaction is the concentration. If you have more molecules present, a higher concentration, well, then more collisions can occur, and the faster the reaction will take place, and the rate will be faster as well. All right, so you can see here, if you have a lower concentration, there's less available molecules to collide and to react, so the rate will be lower. If you have a lot more particles present, you have a greater chance of collisions taking place, and you will have a faster reaction rate. All right, so the concentration here also affects the rate of a reaction. Greater concentration, faster the rate of the reaction. Temperature also plays a role in the rate of a reaction. If you have a higher temperature, you have molecules now that have a greater kinetic energy, which will increase their speed, increase the number of collisions taking place, and also giving them more energy, the energy that's needed to kind of overcome the activation energy here for a reaction to take place. So there's kind of a couple things taking place here. If you have that greater temperature, these molecules are going to be moving around much more, having a greater chance to collide. But not only will they have a greater chance to collide, they will also collide with more energy, all right, and be able to overcome the activation energy needed to react here. So if you increase the temperature, you're increasing the kinetic energy, and you will be increasing the rate of the reaction. If you look here at the picture of this glow stick, if you are actually, if you put a glow stick in a freezer, for example, you can actually slow down the rate of the reaction and make the glow stick actually last much longer. If you put the glow stick in hot water, you would have the reaction taking place much quicker, and the rate would speed up, and the glow stick would be kind of done much sooner. So temperature also affects the rate of a reaction. Surface area also impacts the rate of a reaction. If you have more surface area exposed, you have a greater chance of collisions between particles, so you have a faster rate of reaction. For example, coal dust is actually very explosive, but a piece of charcoal, one lump of charcoal, isn't. All right, so anytime you can have greater surface area here of your reactants, you'll have a faster rate. For example, if you have a piece of magnesium here and you have hydrogen ions kind of hitting that magnesium, trying to react with it, a big piece, the hydrogen atoms can only hit the outer part of the magnesium, all right? But they can't get to the center to react with the center of the piece of magnesium. So now, if you just broke up that magnesium, all right, into pieces, the hydrogen atoms could hit kind of all over the place. There's a lot more places for those hydrogen atoms to hit and react, so the rate of the reaction will be much greater. It will react much faster. So anytime you can increase the surface area, you would expect more collisions to take place and the rate of the reaction to increase as well. Catalysts are the final thing here that can affect the rate of the reaction. If you remember, catalysts are just substances that speed up a reaction, so they speed up the rate of the reaction, but they're not part of the overall reaction. They're there in the beginning, they're there in the end. Catalysts just are simply there to speed up the overall reaction. If you remember enzymes have this lock and key mechanism. Uh, they have this specific shape determined by IMFs, so they're very sensitive to temperature. But the basic gist here of these catalysts, they lower the activation energy and they provide a different pathway for the reaction to take place. And that's how they speed up the reaction. Essentially, they lower that activation energy that's needed, providing a different pathway, and then the reaction can take place at a much faster rate. So you can see here in this picture, if you had to carry the looks like a rock or coal all the way up over this hill and down, that would take a lot more time than just being able to kind of take a different pathway here, a shorter pathway, and kind of just quickly roll it down the hill. That would be kind of an alternate pathway, and the rate of the reaction would be faster here. All right, so that's the job of a catalyst, just to speed up the reaction. This slide is just providing an idea here how enzymes work. You might have, talked about enzymes in biology, but the idea is they have a specific place for substances to bind, and when they do attach, the reaction can take place, and you get your new products forming, and it just allows everything to kind of come in contact perfectly. It aligns everything perfectly, and it speeds up the overall rate of the reaction. And just be careful here. If you're seeing something about an inert gas being added to a reaction, it has no effect on the rate of the reaction. It's a trick, so don't fall for that trick. Anytime you're adding some form of inert gas, like a noble gas, or it says it's an inert gas, it's just there, it has no effect. It's not a catalyst. It's not impacting the rate at all. So don't fall for that trick. This brings us to the collision theory of rates here. The basic gist of this is that when you have particles of the reactant hitting each other, only a certain amount of them actually cause a chemical change. So just because two reactant particles hit each other, that doesn't mean they're automatically going to react. The collision theory of rates here says actually only a certain percentage of those collisions lead to a reaction or lead to a chemical change. Anytime you have a chemical change or a successful change, we call that a successful collision. These collisions have enough energy, which we call the activation energy, to break bonds that are there and then form new bonds. All right. So if you have a successful collision taking place, you have enough energy. You've met the activation energy here, the minimum energy that's needed for the reaction to take place. If you can increase the number of the collisions or increase the strength of the collisions, that's when you can have the rate of the reaction increasing. Anytime you can try to make these reactant particles hit more often and with more energy, you're going to increase the rate of the reaction. But it's more than just colliding. It's not that, oh, two reactant molecules have to collide, and if they collide with enough energy, then a reaction will happen. It's not just dependent on the collision here, as we're going to see on the next slide. As I said on the previous slide, only a certain amount of the collisions between reactant particles actually leads to a chemical reaction, right? Actually leads to a reaction taking place. So you need enough energy, but there's something else here called the orientation factor. Molecules must actually hit a certain way during these collisions in order for a reaction to take place. So not only do you have to have enough energy when you collide, but sometimes here you have to collide in the proper orientation in order for a successful collision to occur. So for example here, if you look at these two molecules here, NO and O3 colliding, if the O from the NO hits the middle O of the O3, as you see here, it's not an effective collision. The reaction will not take place. Even if you spin it around and the nitrogen from the NO hits in the middle there of the O3, it just bounces off. It's going to be an ineffective collision. However, if you have the nitrogen from the NO hitting one of the end oxygens in the O3, then a successful collision takes place and a reaction will actually happen. All right, so just having enough energy here is not enough. You also have to hit in the proper orientation or in the proper place in order for a reaction to take place as well. I want to talk a little bit more about this activation energy. We denote activation energy as E sub A. All right, so E little a stands for activation energy. Anytime you see that, you have to know that that stands for activation energy. And that's the minimum amount of energy you need to start a chemical reaction. If you don't have that activation energy met, a reaction will not take place. Okay, so once these reactant particles collide, there has to be enough energy, and that energy is going to be used to, stretch, bend, and break these bonds in order for the reaction to take place. So we have kinetic energy here being used to change the potential energy in the bonds of the reactants. And basically what happens is once these reactant particles collide with enough activation energy, we get this transition state or this activated complex. It's kind of like this middle state here of when these reactant particles collide. So if you look over here at this picture of the frogs jumping over the rocks here, you can see they have to jump with the right amount of energy to get over the pile of rocks. Otherwise, they're not going to get to the other side. If they leap and they don't have enough energy, they're going to hit the rocks and they're not going to get over it. However, if you could provide a different pathway, if you could provide, say, a catalyst that lowers the activation energy, makes the pile of rocks lower, then it's going to take less energy to get over that barrier, and more of the frogs will get to the other side. So there's a certain amount of energy. We call that the activation energy, a minimum amount of energy that must be met in order for a reaction to actually take place. This activated complex that I talked about on the previous slide, this is just this unstable intermediate state before the products actually form. It's this transition state between the reactants and the products, right? So if we're looking over here, we have our reactants starting the reaction. There's a minimum amount of energy that must be met. You have to hit with the right amount of energy, and then you can kind of go down the other side of the hill here and form the products. But this middle state here, we call this activated complex, or this transition state would be kind of this point that's in between the reactants and the products. The reactants are kind of what you're starting with, the products are what you're ending with, but then this activated complex is kind of the in-between step. And remember, if you don't have enough energy to get over the hump here to get to the products, all right, if you don't have that activation energy, the reaction will not actually take place. It's important to understand graphs like this. So what we're looking at here is we have energy on the y-axis here, and then the progress of the reaction on the x-axis. So we have our reactants here, which is A reacting with B, C, and then eventually when the reaction takes place, we get AB plus C forming. Right? So if you notice here, your reactants start at a certain amount of energy. The energy then goes up. Essentially, you have this minimum amount of energy that must be met. All right, when they collide and they collide with the right amount of energy, you get this transition state or this activated complex that is kind of on the way to the products forming. All right, so this is showing you here the amount of energy that would be needed without a catalyst, without an enzyme. And then the red line here is showing you, all right, the alternate pathway that could be taken with an enzyme or a catalyst here. And you can see it takes much less energy. The hump is much smaller, right? But that transition state is in between the reactants and the product. Notice you start at the same amount of energy and you end at the same amount of energy, whether you had the catalyst or not. All right, whether you had that enzyme there or not, your beginning and ending energy is still the same. Remember, the whole point of a catalyst or an enzyme is to just speed up the reaction, provide a different pathway here for the reaction to take place. And if you notice, this activation energy with the enzyme here is definitely much smaller. Just to summarize this collision theory of rates, remember, just because two reactant particles collide doesn't mean it's going to be a successful collision. Only actually a certain percentage of them lead to successful collisions. You got to collide with the right amount of energy, the minimum amount of energy, the activation energy, and the proper orientation here. Only then will you kind of get to that activated complex and then form the products. Just colliding is not enough. You have to have the minimum amount of energy, the activation energy, and the right orientation in order for that reaction to take place. Let's talk about these reaction rates. Anytime we're talking about the rate of a reaction, we're talking about the change in concentration of the reactants or products over a period of time. So it's the change in concentration over time. Because of that, our units are going to typically be like molarity per second. It's going to be some type of concentration unit per time unit. So typically we see this in molarity per second or molar per second here. You can measure the decrease of the concentration of a reactant or the increase of the concentration of a product over a certain period of time. And you need to understand that these rates of reactions are not constant. They change over time. All right, just because you might start out with a fast reaction rate doesn't mean that that same reaction rate will continue throughout the reaction here. So that's very important to understand. Notice if you're starting this reaction here with one reactant, looks like the red is A, and over time you start to see A is slowly disappearing and B is forming, and then as time continues, A disappears even more and B is forming even more. So the reactants are going to disappear in our reaction and the products are going to appear here. So it's very important you understand that these rates of reaction are changes in concentration over time. So our units are typically going to be molar per second. All right, so we already know that the rate of reaction is going to be the change in concentration over the change in time. So if we want to look at the rate of appearance of a product, essentially what we're going to have is the change in concentration of the product over the change in time. So if we have this reaction taking place here, A going to B, we have our initial time, and then we have the time we're measuring 20 seconds later. We have an initial concentration of substance B, and then we have kind of our final concentration of substance B. So if we wanted to find the average rate here all right? It's an average rate. We just take the change in concentration of the product over the change in time. So we ended with 0.46 molar. We started with 0 molar. So you'd subtract those to get your change in concentration. We ended with 20 seconds. We started with at 0 seconds. So if you subtract them and then divide, your average rate over this 20-second interval for the rate of appearance here of the product would be 2.3 times 10 to the negative 2 molar per second. All right, so that would just be the average rate of appearance of this particular product. Remember, anytime you're doing a rate, it's a change in concentration over the change in time. If we wanted to look at the rate of disappearance of one of the reactants. Remember, reactants are disappearing here. They're going to be used up and the products are going to be formed. So it's still going to be the change in concentration over change in time. You just need to realize here that these are being used up or they're disappearing. So it's negative, the change in concentration of the reactant over the change in time. So again, same reaction here. You could see your time intervals and your concentration data. If you want to find the average rate, just take your change in concentration over your change in time. When you subtract them, all right, pay attention to your negative here because the reactant is disappearing. You get, again, 2.3 times 10 to the minus 2 molar per second. All right, so the reactant is disappearing essentially at the same rate that the product is appearing because it was a 1-to-1 ratio here. Again, this is just an average rate of the reaction, looking at a change in concentration over the change in time. And just remember, your reactants are used up. If you look at this graph, you can see that the rate of the reaction is not constant over time. It can change. And typically what you see taking place is that the rate of a reaction will usually slow down as the reactants are used up. And that makes sense. As you get less and less reactants available, you have less and less concentration of those reactants. There's less chance of having two reactants collide. So you would expect the rate of the reaction to slow down. So over time here, if you're looking at this particular reaction, you can see the rate starts to slow down. And that makes complete sense. As your reactants are used up, you're not going to collide as much. You're not going to have those successful collisions taking place as much. So the overall rate of the reaction would decrease. If a particular reaction is 1-to-1, we already know that the rate of appearance of the products would be equal to the rate of disappearance of the reactants. However, if it's not 1-to-1, you need to take into account here the coefficients of the reaction. So for example, if you have this reaction taking place right here, A plus B going to C and D, and these letters in front, little a, little b, so on, those are the coefficients that go with each of the reactants and products. So your rate here, remember, your rate is a change in concentration of the reactant or product over the change in time. So if you wanted to do the rate of disappearance here for reactant A, it would be negative 1 over little a, essentially 1 over the coefficient in front times the change in concentration of A over the change in time. So you just take 1 and put it over the coefficient. But remember here that the reactants are disappearing, so they're negative. Same thing for B. It'd be the change in concentration of B over change in time, but it's negative 1 over the coefficient in front of B. And then the products are formed, all right? So you take the coefficient in front, and it's just 1 over that coefficient times the change in concentration over change in time for that particular product. Remember, they are forming, so they're positive. Sometimes you might have to actually use this in problems to be able to solve for a particular rate. And you'll see how we can do that here in a second. If we look at this particular graph, you can see that this graph is for the decomposition of NO2. So the reaction is written up here. You have 2NO2 decomposing into 2NO plus O2. If you notice here, even if you didn't necessarily know the exact reaction, you would know that the NO2 is the reactant because you can see over time, all right, the concentration of the NO2 is going down. That's what you would expect to happen for the reactants. So even if you weren't explicitly told that that was the reactant, you could analyze this graph and figure it out because it's decreasing. And then notice the O2 and the NO are both increasing over time. Well, that's what you would expect to happen for the products here. And just take note that the NO is actually forming twice as fast as the O2. And that makes sense because according to the balanced equation, there's 2 NO for every 1 O2. So you need to be able to look at a graph like this and understand that the reactants are used up over time, the products are formed over time, and realize you can even see the stoich involved here as well. Just want to show you here a quick example. I have it completely solved for you, so I'll walk you through it. It says for the reaction of 2O3 going to 3O2, we want to write the rate expression, and given the rate of O2 is 6.0 times 10 to the minus fifth molar per second, what is the rate of O3 disappearing? All right, so remember now, this is not one-to-one, so the rate here would be equal to, for the reactant, you'd have negative 1 over the coefficient. So negative 1 over 2 times the concentration of the O3, change in concentration of the O3 over the change in time. And that would be equal to 1 over the coefficient in front of the product. But remember, this is positive because it's the product it's forming. So 1 over 3 times the change in concentration of that product, the O2, over the change in time. So what we're trying to figure out here is the rate of O3 disappearing. Well, that rate of O3 disappearing is the change in concentration over change in time. Basically, you're solving for this piece right here. So you basically plug in what you know. You know negative 1/2 here times that rate, which you're solving for, would be equal to 1/3 times the rate of the O2 forming, which they told you the rate here of the O2 forming is 6.0 times 10 to the minus fifth molar per second. So all you're doing here is solving for this rate. And when you plug and chug that, you get 4.0 times 10 to the minus fifth molar per second, right? So being able to write the rate expression here from an equation and then realizing, hey, look, the change in concentration over change in time, that's a rate, right? They might ask you to solve for that for one of them, but you need to be able to kind of create this, realizing the reactants here are going to disappear, the products are going to form, and pay attention, they do 1 over the coefficient in front of the reactant or product. This is your chance here to try one of these. This particular one says if the rate of disappearance of N2O5 is 4.2 times 10 to the minus 7th molar per second at a particular time, what is the rate of appearance of NO2 and O2? All right, so I want you to try this on your own right now. Write out your expression, plug in and solve, and you can pause the video right now and try it. And when you rejoin, I'll have it solved for you. So right now I would pause the video and try it. Okay, so hopefully these are the answers you got here. I set up my kind of rate equation here, knowing that I have 1 over the coefficient for each times the change in concentration over change in time. So I solved for the rate of O2 here first, using, plugging in what I knew from the problem. And then because I saw that once I know the rate of O2, I know that the rate of NO2 forming is going to be 4 times that value because of the stoich here. So once I found the rate of O2, I just multiplied that by 4 to get the rate of the NO2 because I knew it was going to be 4 times faster. So this is a pretty basic way of using rate data and the change in concentration over change in time in order to solve for the rate of appearance or disappearance of a reactant or product.